Okay, let's look at some examples of calculating the spherical harmonic functions from the general formula. So let's look at these examples. Let's calculate the functional form of y00, y10, and y11 as a function of both theta and phi, and then we'll try and figure out where these functions are maximized and minimized. So let's start with y00. So y00, I can just write it generally from the general expression as a00, e to the I 0 times phi, and so that's just going to give me a factor of 1. And then p00 of cosine theta. So I need to figure out what p00 is as a function. And so let me just calculate what p00 of x is. Just forget about the cosine theta for now. So p00 of x is 1 minus x squared all to the 0th power. Okay, so that's just giving me 1. d by dx to the 0th power. So again, that's just going to give me 1, no derivatives. And then times p0. Well, p0 is just 1. And so p00 is also just 1. So all of these are just constants, in fact, just factors of 1. And so all I get is a00. Again, this is a constant you can look up. For our purposes, all we need to know is that there's no angular dependence to this. And so you can think of this as essentially being a sphere in this sense that the function, the y00, doesn't have any angular dependence. It's the same in all angular directions. Okay, let's look at something a little bit more interesting. Let's look at y10. So y10, I can write as a10, e to the I m times phi, where m is now 0 again, p10 of cosine theta. Okay, so p10 of cosine theta actually looks a lot like p00 of cosine theta, in that the 1 minus x squared factor is just 1. There's no derivatives, d by dx to the 0, so that's just 1. So all I pick up is p sub 1 of cosine theta. Well, p sub 1 of x is x, which means p sub 1 of cosine theta, again, the rule is I just place cosine theta wherever I would have had x before, and so I just get cosine theta. So y10 is just some normalization constant times cosine theta. Well, what does this look like? Well, what it means is that the largest probability for this function is at 0 and pi, and there is 0 probability of finding something at pi over 2. And again, just reminding ourselves that spherical harmonics here in quantum mechanics are telling us about probabilities. And so we can interpret the values of the y0s as probabilities of telling us where we're more likely to find a particle in three-dimensional space or not. And so here, again, we see the largest probability at 0 and pi, and essentially 0 probability at pi over 2. So it has this dumbbell-like shape. Okay, finally, let's do y11. So y11 is a11. Again, some constant, e to the I phi. So now we actually get a phi dependence here because m is equal to 1. And then p11 of cosine theta. So p11 is actually a non-trivial associated Legendre function. So we really do have to calculate this. And so in order to calculate this, we'll take 1 minus x to the 1/2, which turns out to be a square root. And then the d by dx has an exponent of 1, so I just have a single derivative, d by dx, of p sub 1. P sub 1 is just x here. Okay, so altogether, p11 is the square root of 1 minus x squared, d by dx of x. Well, the derivative acting on the x just gives me a factor of 1, so that takes care of itself there. And so all I'm left over with is the 1 minus x squared. But I really have to replace x with cosine theta everywhere. And so what I get for y11 is a11 e to the I phi, and then the square root of 1 minus cosine squared theta. But I can simplify that 1 minus cosine squared theta into a sine theta. And so I really have a11 e to the I phi times sine of theta. Okay, so what does this mean in three-dimensional space? So in three-dimensional space, okay, so theta equal to 0 is right along the z-axis, and so we would have 0 probability of finding a particle there, since sine of 0 is 0. And same thing for sine of pi. Along the negative z-axis, I would not find the particle. But I would find the particle at, say, theta is equal to pi over 2. That'd be the highest probability of finding the particle. So if I interpret that in three-dimensional space, it looks like I should get something that looks like a torus here. Notice that the e to the I phi, I'm not doing anything with the e to the I phi. I'm actually just taking the absolute value here, and in taking the absolute value, the e to the I phi vanishes, and so this is still symmetric as a function of phi. So I get this torus-like structure in that it's more likely to find the particle at pi over 2 instead of at 0 or pi, as it was for y10. So we can see that these different quantum numbers, these L and M quantum numbers, lead to really different probabilities of finding a particle in a particular location. You may find it along the plus or minus z axes here, or you may find it along the equator. And it's important to keep track of that theta and phi dependence to get into your head a conceptual picture of what's happening with the wave function. Okay, I hope this gave you some experience with calculating with spherical harmonics and seeing how to use this general formula for the associated Legendre function.